Hello student, good morning. I am Dr. Sinha, Professor of Chemistry. Today I am going to continue from the last class. Now I am going to discuss effect of temperature on rate constant. Effect of temperature on rate constant. Last class I have discussed pseudo unimolecular reaction. Most of the chemical reactions are accelerated by increase in temperature. For example, in decomposition of N2O5, the time taken for half of the original amount of material to decompose is 12 minutes at 50 degrees centigrade. 12 minutes at 50 degrees centigrade. That is the time for decomposition. At 50 degrees centigrade, you have to here give importance for the temperature. And 5 hours, same reaction means decomposition of N2O5. It takes 5 hours at 25 degrees centigrade and 10 days at 0 degree centigrade. 3 temperature just you consider. It is actually experimental value that decomposition of N2O5, the time taken for half of the original amount of material to decompose is 12 minutes at 50 degrees centigrade, 5 hours at 25 degrees centigrade, and 10 days at 0 degree centigrade. Then here you know actually that in a mixture of potassium permanganate means KMnO4 and oxalic acid means H2C2O4, potassium permanganate gets decolorized faster at higher temperature than that at lower temperature. This is another example. Mixture of potassium permanganate and oxalic acid. Potassium permanganate gets decolorized faster at higher temperature than that at lower temperature. It has been found that for a chemical reaction with rise in temperature by 10 degrees centigrade, the rate constant is nearly doubled. It is actually observed. It has been observed that for a chemical reaction with rise in temperature by 10 degrees centigrade, the rate constant is nearly doubled. Means only by increasing 10 degrees centigrade, rate becomes double. The temperature dependence of the rate of a chemical reaction can be accurately explained by Arrhenius equation. It was first proposed by chemist J.H. Van 't Hoff, but Swedish chemist Arrhenius provided the physical justification and interpretation. K is equal to, K means here rate constant, K is equal to A is a capital, K is equal to A exponential minus EA divided by RT. This is the rate constant according to Arrhenius. Okay, according to Arrhenius, K is equal to A, capital A, into E. E means exponential, small e power EA divided by RT, where A is the Arrhenius factor, also called frequency factor. This question is asked in examination. What is the A? A is the Arrhenius factor or the frequency factor. It is also called pre-exponential factor. Third, you can say term is also there, pre-exponential factor. Means A is known as Arrhenius factor, second also known as frequency factor, and third also known as pre-exponential factor. It is a constant specific to a particular reaction. R is a gas constant, R is a gas constant, and EA, capital E and down small a, EA is activation energy measured in joules per mole. Joules per moles. Then now here all things you are knowing. T is the temperature. T is temperature. Then here in this expression all terms now I have told you what they mean. It can be understood clearly. How we will understand the by one example you can understand. That is the H2 plus I2, that is 2HI. H2 plus I2 gives a 2HI, hydrogen iodide. All are in gaseous state. H2 is in gaseous state, iodine is in gaseous state, and HI formed is also in a gaseous state. Okay. According to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. H2 plus I2 directly it will not give HI. Directly it will not give HI. Before giving HI, one intermediate it forms. That is that you have to understand here. Here you can write H2 and I2 like that, HH. Okay, HH bond you have to show, plus I bond you have to show. Correct? Can't write H2 plus I2, H and HH one bond you write, plus I and I bond you can write. Here what will happen, before giving to final product, this HH and I they will come close. Okay, both molecule will come close. Means both H will come close with both I, and they will make a weak bond between H and I. 2H is there, 2I is there. Then both H and I will come closer and they will make a very weak bond, HI bond. And HH bond will not break that time fully. It will also become weak. I bond also become weak. And new bond will begin to form, weak bond. Between H and I, means at intermediate step or stage, bond is not broken completely. They are only there, it is going to be weakened. Both HH bond will weak, I bond will weak, and new bond it will form, that is also weak. HI means total 4 bonds. At this stage, intermediate stage, 4 bonds will be there. HH, I, and a new bond formed, HI between H and I. But all these forms are weak. But with the time, this original bond of HH and I will slowly and slowly will become weak, and finally at intermediate stage it will break and it will convert to HI, means it will form 2HI. HI and H plus HI. 2HI it will give. HI plus HI. Then here this happens at intermediate stage. Okay, according to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate. It exists for a very short time, but intermediate it will form for short time, and then breaks up to form the molecules of hydrogen iodide. Okay, then this here the term collision now is used. Collision, this H2 and I2 will collide and it will form intermediate stage for short time, and then it will convert to final product. Okay, the energy required to form the intermediate called activated complex. The energy required to form the intermediate, it forms the intermediate, then energy required to form the intermediate called activation energy, or you can say this the energy required to form the intermediate called activated complex, and energy, what is the energy? Activated complex, and that energy actually is known as activation energy, EA. EA. Now I want to brief it. Here what happens, already once I have discussed, now again I am telling you, there are three terms you have to use. First term is threshold energy. Okay. Second term is energy possessed by the molecules, and third term is energy of activation or activated energy. All three are related. All these three terms are related. Actually what happens, that gaseous molecules in the beginning, means before a reaction, they have some energy. Then that energy is called energy possessed by the molecules itself. After that, they want to react with other molecules. Then for this, they require to form activated complex. For that, they require more energy. Then how will they get this energy? They have less energy. But for the reaction, means to form the intermediate, it requires more energy. Then how will it get? How will they get this energy? Then for that purpose, they will collide itself. Due to the collision, energy increases. Then actually intermediate stage, just it is, you can tell it is a barrier between reactant and product. Before giving to product, it has to cross through this energy barrier. Energy is high energy is required. Okay, just from the low energy it will go to high energy curve. Now high curve, again it will, after the intermediate, it will give the product, means energy will lose. Again it will, just like a wave, it will go up and it will go maximum, again it will come down, and then it will convert to the product. And now here you can understand very easily what is the activation energy. Here that just simple example, suppose you want to purchase some things, its cost is 1000 rupees. In your pocket 200 rupees is there. Then now we need 800 rupees. Then you can purchase the any item as per your desire. Then 800 is actually, that is the requirement. 800 is requirement. Then here in gaseous molecules same things happen. Molecules will have some energy by own. That is the energy possessed by the molecules itself. Now this 800 is actually called energy of activation or activation energy. Then both, if you will add this 200 plus 800, then it will be 1000 rupees total. Then this total energy is called threshold energy. Threshold energy, THRESH, threshold, HOLD, threshold energy means threshold energy is equal to energy possessed by the molecules itself plus activation energy. This relation don't forget. Threshold energy is equal to energy possessed by the molecules itself plus activation energy. Then here at the top, when intermediate is going to be formed after getting this extra 800 energy, then there actually old bond will begin to break and new bond same times it will begin to form. Then it happens for a short period. Then that complex formed, just like HH bond is becoming weak, II bond is becoming weak, and new bond HI is forming. Then in a short period this happens, complete HH bond will break and II bond will break and new bond HI will form. Then all four bonds, two bonds are old bonds and two new bond. Then all four bonds will be present at intermediate stage. That's why it is called activated complex, because they are active, they are about to break. This stage is also called transition state, because now reactants are going to convert to product. Then it is also called transition state. Then now after crossing this energy barrier, intermediate stage or transition state, the energy then high, because it requires more energy, that's why it is called energy barrier. Then now you understood what is the activation energy. Now here just you can understand that by diagram also you can understand, by plot, that is the potential energy versus reaction coordinate. By one plot you can understand that is the potential energy versus reaction coordinate. Reaction coordinate, that is our x-axis, and potential energy y-axis. Okay, down means x-axis horizontal and vertical is y-axis. Then here you have to understand how to plot it. Then you should start making these things plot. Suppose reactant is A and product is B. Then A has some energy. That's why you can't start from the zero. You start little above, because A has some energy. Okay, then you can start a curve just little above from the zero, little above from the zero, because they have some energy. And after that, you can say it will go. You have supplied the energy. You can heat it, then also reaction can take place. Collision will be more. Okay. By heating, if you will heat it, collision will be more. Then now potential energy will increase. Slowly and slowly, potential energy will increase, and it will reach to the top. It will reach to the top, just like a wave. Slowly and slowly it will go up, and it will reach to the top, means energy barrier it will reach. And after that it will give, after that it will come down, curve will come down, correct? Then where it will stop, curve will come up to what stage? Below A or above A. Reactant is A, then curve will go, both possibilities are there. It can come down below A also, but product side. Okay, it is just like a wave. It went up, after top it is becoming slowly and slowly down. Okay, reaction intermediate will see coordinate, then it will be far from A, B will be far from A, and then two conditions are there. This curve may stop before A, or up or below A also, above A also, below A also. Then where it will stop? Two possibilities are there. Then first possibility is that if reaction require, you can say product require less energy, then it will stop above the A, correct? And if you can say product requires less energy, then it will come down, because coming below A means potential energy is less than A. It means what? Excess energy it will release. Means between A and B is coming down. Means down means less energy. A is more energy. It came less than A. Then between A and B, what is the energy gap? That energy it will release. That energy called exothermic reaction. And when it will be up, means above A means product is require more than A energy, correct? 200, as for example I told you that 200 was having, but now this product required less energy, more energy, more than A. Suppose it requires 700, then 500 is required extra. That's why you have to heat it. Then it will go to the energy barrier, and then it will come down, because product requires more energy. That's why you are heating. Then that is called endothermic reaction. Correct? Then how much energy it will this thing require? Then 200 suppose it was having, and 700 was required. Then 500, now you can say this energy you have to supply. 500 energy means joule, anything unit of energy. That is required. That's why you have to heat it. Correct? Then now it will give the product. And if they require less, if B means product required less than A, then in that situation, that what is that, suppose now it requires only 100, and they have A have 200, and requirement is only for 100. Then this 200 minus 100, that is equal to 100. Then that amount it will release. Okay, after when it will convert to the product, then this 100 it will release. Because only 100 is required, you have 200. 100 it will release as a exothermic reaction. Then this potential energy difference between A and B, that is actually whether reaction is exothermic or endothermic, you can understand by seeing the energy gap. If it is down below A, less than A, then exothermic reaction. If more than A, product require more than A energy, then what is the difference? 200 they have, 700 want. Then 500, 700 minus 200. Okay, product side means down when this just like a wave, it will go up, will come down. That side you will find product is above. Above means energy required more than A. That's why you have to heat it, endothermic, and it will come down below A. Then how much difference is between A and B? That small distance, that energy it will release. That is called exothermic reaction. Okay, I think now we understood all the things. Now another things I want to tell you. Okay, the energy required to form the intermediate called activated complex is known as activation energy, EA. E means energy, small a means activation. And by this graph I already have discussed. Reaction coordinate represent profile of energy change when reactants change into products. Some energy is released when the complex decomposes, means activated complex. Some energy is released when the complex decomposes to form products. So the final heat of the reaction depends upon the nature of reactant and products. All the molecules in the reacting species do not have the same kinetic energy. Every molecules have different energy. Here you have two important point. All the molecules in the reaction species, means reactant I am talking about, reacting species do not have the same kinetic energy. Since it is difficult to predict the behavior of any one molecule, it is very difficult. Okay, since it is difficult to predict the behavior of any one molecule with precision, then what you will do? Boltzmann, one scientist is there, L. Boltzmann, that is his name was Ludwig Boltzmann, and other James Clerk Maxwell, two scientists, Boltzmann and other is called name is James Clerk Maxwell. Shortcut you can tell Boltzmann and Maxwell. Used what they used statistics to predict the behavior of the large number of molecules, because in gaseous molecules very large number of molecules will be there, even you can't see, so small. Then according to these two scientists, the distribution of kinetic energy may be described by plotting the fraction of molecules. Fraction of molecules means what here? Fraction of molecules with a given kinetic energy E versus kinetic energy. Means here you have to make a plot to understand the energy. Then it is described by plotting the fraction of molecules with a given kinetic energy versus energy. Okay, then here that is the fraction. I am telling about the fraction. Okay, then fraction means here molecules have, you know that molecules have different energy. Then here one can say any time you can tell energy divided by nt, ng upon two types of energy they will have. Okay, means at a particular time, what is Ne, that is energy is called Ne. Okay, and divided by Nt, Ne divided by Nt with a given kinetic energy. Means you have to draw the plot, that is a fraction of molecules versus kinetic energy. Then that fraction is a ratio of Ne divided by Nt. Okay, then here Ne, what is the Ne? Ne is the number of molecules with energy E, and Nt is total number of molecules. Nt is the total number of molecules, and Ne, which is Ne upon Nt, then Ne is the number of molecules. Both are number of molecules. Then here Ne is the number of molecules with energy E, and Nt is the total number of molecules. Here just you can understand, say by a general example. 100 students are taking part in a running race, and in that it is observed that few students only, they are running very fast, but their number is very less. Those who are running very fast, their number is less. Out of 100, maybe 10 students. 10 students are running very fast. 10% are running very fast. Then out of 100, this who is running fast, their number will be less. Correct? Then here in plot you are knowing these things only. Total 100 students. 10 students are running very fast, and other students are, most of the students, their speed is less. They are running slowly. Then you can draw a graph in this way. Down you can write, that is the student who are, number of students who are running fast, means having more energy. Then what you will find? Top will be less. It has started with 0, then all students are running. Hence, with the time, their speed may increase. Then slowly and slowly, means speed will increase. Here speed means energy. Our student means molecules. You can understand like that. Then that maximum molecules, slowly and slowly, its speed will increase. But you will find that with the time, that only few students are running very fast. Few students. Then that is means 10 students. Then 10 out of 100. That is the fraction. Both are number of students having energy E, and divided by total, you can say this student, total number of a student. Then 10 divided by 100, that is the fraction. Then here you will find by the plot that number of students whose energy is more, means running fast, that number is less. Then x-axis energy graph is there. X-axis is of kinetic energy, and y-axis means vertical, that is the fraction of molecules. Then fraction of molecules will be less. Fraction of molecules having more energy, then that will be less. Okay. Then here this fraction you will find that kinetic energy will be highest only for some molecules. Only for some molecules kinetic energy will be highest. Correct? It will be top. That is the top position. Okay, there after that what will happen? Again with the you can say time, with the time, that again you can this other molecules, their number will be less only. Their number will be less only. Then only some gaseous molecules will have maximum energy. That energy, maximum energy, that is called most probable velocity. They have highest velocity, but their number will be whatever be number. Now forget, you understood that some molecules will be run very fast. Then here in gaseous reaction, it has been seen that fraction of molecules having energy E will be highest. Okay, at this position, means fraction of molecules will be highest. Okay, in the beginning it will be less molecules, fraction of molecules in the beginning it will be less with the time, and as the time will go, and slowly fraction will increase. Whose energy is increasing, that fraction will increase. Okay, gaseous molecules, their speed will increase, velocity will increase with the time, and a time will come, then some gaseous molecules will reach to the highest fraction. Now suppose in the beginning it was 20, then it reached to 30, 40, 50, 60. They reached that maximum 60 molecules. Now they have reached to the highest energy, highest speed, highest velocity out of 100, 60. Correct? This fraction 60 by 100. Now what is their molecules? Means maximum fraction, suppose 60. They have maximum energy, maximum fraction, that is a fraction of molecules having maximum speed, that is called most probable velocity. Okay, means fraction of molecules who have maximum speed, maximum velocity, then that you can say how much energy they have, maximum, that is called maximum velocity, because they have maximum energy. Then it is also just like a this all wave only. It start with 0, slowly fraction will increase. It will go to the maximum fraction. Y-axis you can compare maximum fraction, and after that again with the time you will find that their fraction is decreasing, and it will become so less, but it will not touch the x-axis. It may be just like a parallel. when it will come down on axis, it will just like a parallel, it will not touch. These things you understand that this you can say maximum kinetic energy means maximum velocity that time, correct? And that point, top point, what is the, you can say, where it is meeting to the y-axis, that is a y-axis means fraction of molecules, that you can know that how many molecules have highest, highest velocity, that by the graph you can know, correct? If your data is with you, you can know that fraction of molecules, fraction or number of molecules having maximum energy, number of molecules having maximum energy means fraction of molecules means out of total NT, out of NT, NE is the fraction which have highest energy, okay, or highest speed. Then that actually, that speed or that velocity, that is called most probable velocity, okay. Actually this is called distribution curve. This is called a distribution curve, because in the beginning fraction was less, it increased to the maximum like 60%. After that again slowly and slowly it came down, and it is not touching to the y-axis. With the time energy is decreasing, means fraction of molecules, it is decreasing with time, and energy is also decreasing, but it is not coming zero, because you know that molecules have some energy, molecules themselves have some energy, okay, it will not be zero. Then this I told you about the, I can say, distribution curve, is also called distribution curve. That is the fraction of molecules versus kinetic energy. This is given by the Boltzmann and Maxwell. Okay. Now again I am telling you the peak of the curve. The peak of the curve correspond to the most probable kinetic energy. Okay, whatever be fraction, 70%, 80%, whatever be, that fraction have maximum velocity, that is called most probable kinetic energy. Peak is actually called. From the peak, just to draw a line parallel to y-axis, it will come to the x-axis. From the top peak to the x-axis, draw one line parallel to y-axis. Then whatever is the energy, that you will come to know that this maximum fraction, how much energy, what is the value of kinetic energy, you will come to know. Okay, kinetic energy of maximum fraction of molecules, you will come to know. Most probable kinetic energy means kinetic energy of maximum fraction of molecules. Okay, there are decreasing number of molecules with energies higher or lower than this value. Just it is very clear cut, very conceptual, that peak is the highest in terms of both, in terms of energy, also in terms of fraction. Then before peak fraction was less. Before the peak, fraction was less and energy was also less. And after the peak, because it is coming down after the peak, then again it is because it is coming down, then fraction will be less, energy will be also less. Then peak is the highest, where maximum molecules have maximum molecule fraction have maximum energy. But before and after this peak, in both situations it is less. Fraction will increase slowly and slowly before reaching the peak. Fraction will increase, energy will also increase, but it will be less than peak, and after the peak again this fraction will decrease and energy will also decrease. Means peak is the highest for in both cases, in term of fraction, in term of energy. Okay, this I have told it is very conceptual. There are already told you there are decreasing number of molecules with energies higher or lower than you can say peak, higher or lower than the value. When the temperature is raised, now you can see another condition I am telling you, which actually you require here. Effect of temperature, now you can understand here. When the temperature is raised, the maximum of the curve moves to the higher energy value, and the curve broadens out, that is the spreads to the right, such that there is a greater you can say this proportion, greater proportion of molecules with much higher energies. Means here now if you will increase the temperature, then what will happen? Actually in the beginning peak was there, peak was there. Now you are increasing the temperature, then one graph already you have seen, peak maximum was there. Now if you will increase the temperature, then what will happen? That now maximum gaseous molecules will have more energy. Okay, because energy you are supplying, heat you are supplying, then it will be broaden. Graph will become broaden. Means now maximum molecules will have high energy. Means now peak will become less. Okay, less than the first peak. Now second graph, nature of graph, second, now you find it is becoming broaden. Means now more molecules, fraction of the molecules, their fraction increased. Suppose that time it was 60, now 70, 80% you can tell. Gas molecules are now having more energy. Okay, but their fraction, these things, fraction you can tell, not fraction you can tell, that energy fraction actually decreased because it is becoming broaden. Then fraction of the molecules having more energy, that decreased. Energy is becoming more, but fraction that is decreasing in the second graph. It is becoming broaden. Correct? Then fraction of the molecules having more energy than peak. I am telling about. Okay, their number fraction is increasing now, having more energy, because kinetic energy, x-axis kinetic energy graph is there. Then it is becoming broaden. Then this fraction decreased, but their energy increased. You just to see the graph, x-axis, it is going to the right, means energy is increasing towards right. Then now graph is down, second graph is down, means this decreased, fraction of molecules decreased, and but their energy have increased. Correct? That is observed. Okay, and here you will find that first graph, it was coming very close to the x-axis, but it was not touching. It was not touching to the x-axis. It was little becoming parallel to the x-axis, but not touching. From the top it was coming down, and the end it became little parallel to x-axis. But the second graph, when you increase the temperature, then what is observed, that second graph, that when it is coming closer to the x-axis, but it is above the first graph. Second graph, now when it is coming down to the x-axis, but it is above the first plot. Okay, x-axis, this first plot was very close to the x-axis, but now second graph, now they are going little more high. It is not touching. It is not touching to the, you can say this second, even means little above the above of the x-axis, but it is above the first plot. Both are now coming close only, but it is above the first plot. Second plot, which is coming down, that is above the first, little above. Then now you can see it is becoming to the extreme right side, it is happening. Means it is above the second plot which is coming down to the x, that is above the first plot. Then if you will make it you can say some dark, then you will find then in the first plot, number of molecules, I told you, that was less. Right side, with the time you know that energy increase, but fraction will decrease. Fraction who was having more energy, fraction of molecules whose energy is very high, their number is very less, because it is a right side. On kinetic energy, x-axis graph, right side means more energy. Left side is less energy, right side is high energy. But in vertical, down is less fraction, above is more fraction. Then here you will see that zero, near the zero, when plot is coming down, then fraction is coming closer to zero, but not zero, 10% I think above. 10% above is their first graph. Only 10% molecule was having more than 0. But here in second graph, now it is becoming 15%, 16%. Correct? Fraction is more after heating, who have highest energy, more energy in comparison to the first. In the first graph, you have not heated. In second graph is after heating. Then now it is observed that fraction of molecules having more energy increased in comparison to the first plot. That time suppose it was 10, then now it is becoming, after heating, fractions who have more energy, right side of I am talking about x-axis, right side axis means more energy. Then now it becomes 17%, whose energy is more than first plot, first graph. Okay, here only you have to understand that is actually effect of heating. Means if you are heating, then energy is increasing. Means fraction of the molecules, means more molecules will become, you can say, activated. More collision will take place, and activation energy, now forget now this activation energy, now come to that point, that fraction, number of molecules whose kinetic energy is more, that increased. that increased after heating. Okay, kinetic fraction of the molecules increased after heating. Now they have more energy in comparison to the first one. Okay, and now I have told you this is actually also called a distribution curve. Distribution curve showing temperature dependence of rate of a reaction. Correct? Temperature down will have more temperature, up will have less temperature. Both graph only in one diagram you have to show. Okay, total three diagram I have discussed. Then first one was simply that is the potential energy versus reaction coordinate. In that I discussed about the activation energy. Second, I have discussed fraction of molecules versus kinetic energy. And third, that is effect of temperature. Effect of temperature. Okay. Then here shadow you can put some dot point one point you will write between the first and second graph near the x-axis far right side. Then that dark will tell about the area. This area shows fraction of additional molecules which react at suppose 10 degree you have increased, T plus 10. In the beginning it was T, now 10 degree you have increased. Then this, how much molecules increased? Then I told you, suppose it was in the beginning 10%, now it becomes 17%, then 7% increased. Then this shadow line between the two graph near the x-axis, that area shows fraction of additional molecules which react at T plus 10 degree. Suppose you have increased the 10 degree only, it will be actually observed, rate will become roughly doubled. Okay. Then this I have discussed that at high temperature collision will be more, and if you increase the 10 degree temperature, then experimentally it is seen that rate become doubles. Okay. The area under the curve must be constant, since total probability must be 1 at all time. That is also correct, that this the area under the curve that must be constant. Why? Since total probability I am talking about, total probability must be 1. Correct? Always a probability may be in fraction only 0.1, 0.2, 0.3, 0.4 like that, maximum 1 at all times. When we can mark the position of EA on Maxwell distribution curve, there you can pick position, Boltzmann constant, you can give a mark also, that will tell about the maximal Boltzmann distribution. The maximum curve, where is the maximum curve, this fraction, there you can mark it. What its energy, that also you can mark it. Okay, next I am telling you, increasing the temperature of the substance increases the fraction of molecules which collide with energies greater than activation energy, means EA. Here should understand, increasing the temperature of the substance increases the fraction of molecules which collide with energy greater than EA. By graph it is clear. Okay, because it is above, second graph is above the first graph, that means same things. Okay, it is clear from the diagram that in the curve means T plus 10, the area showing the fraction of molecules having energy equal to or greater than activation energy. Activation energy, either it will be T plus 10. I am talking at T plus 10. The area showing the fraction of molecules having energy, that energy will be either equal to activation energy, what they require, or greater than activation energy. Okay, that actually, if by the further 10 degree rise in temperature gets doubled, leading to these things, doubling the rate of reaction. Okay, if 10 degree will increase, rate will become doubled. Now in the Arrhenius equation, a factor is there, e power minus Ea upon RT. Always remember, e power minus Ea upon RT. What does it means? In the Arrhenius equation, the factor e minus small e means exponential power minus E upon RT correspond to the fraction of molecules that have kinetic energy greater than Ea, capital Ea, activation energy. Important thing, this what does it mean? Fraction. Okay, then factor exponential E minus E upon RT corresponds to the fraction of molecules that have kinetic energy greater than Ea. Okay, then if you will expression, that K is equal to this things, A, capital A into E minus K upon RT, that is the Arrhenius equation. Now if you will take logarithm, both side, then what will happen? K will become ln K, natural logarithm we are taking. Then K will become ln K, and left side become ln K, and right side, that is equal to, means ln K equal to minus Ea upon RT plus ln A, capital A. Correct, because A was there in the beginning, A was there. Then now you can separate it, ln A plus minus Ea upon RT, because this is the power will come down, then it will come Ea upon E will cancelled out, if you multiply by ln, then E and ln will cancelled, then only what will remain? Only minus Ea upon RT will remain, and plus ln A is the, that constant, A is constant. Okay, exponential factor already I have discussed. Then now this you have seen that how this Boltzmann, how that this Arrhenius equation, now you just after taking the logarithm, now it has converted into ln K, that is equal to minus E upon RT plus ln A, where ln is a frequency factor. Okay, frequency factor already I have discussed. Then now further you can understand that Arrhenius equation, that actually better you understand by concept. Both way you can understand Arrhenius equation. According to Arrhenius equation, you can understand that increasing the temperature or decreasing the activation energy will result in the increase in the rate of reaction. Just try to understand, increasing the temperature. Obviously, if you increase the temperature, then collision will be more. Or that if you will increase the temperature, then you will get activation energy. Quickly you will get activation energy. What is the required? That will become less. Okay, what is the requirement? Now we are getting that energy, then quickly it can cross, means activation energy, an energy barrier was there, now energy is increasing, then you will reach quickly. You will reach quickly that barrier, means activation energy will decrease by increasing the temperature. Increasing the temperature or decreasing the activation energy means a peak are becoming a down, then it is decreasing, activation energy is decreasing. Then increasing the temperature or decreasing the activation energy will result in increase the rate of the reaction and an experimental increase in the rate constant. Okay, then obviously rate constant will increase. Rate constant will increase. Now actually you can draw one more graph. This time ln k versus 1 upon t graph, because that this I told you equation ln k, that is equal to minus Ea upon RT plus ln A. Now you want to know the value of actually K and A, like last time I have discussed. That value you will get in the same way, only just minor change is there. Now you want to know K value, you want to know A value, you are not knowing. Then if you will draw the graph ln K versus 1 upon T, then you will get two things. First things, you will get ln K value, means ln A value you get. By this graph, ln K versus 1 by T, that slope, it gives actually a straight line. Then that slope, it will become just a right angle triangle only. Then this H, hypotenuse, that is called slope. Then slope is equal to minus Ea upon R. Already I discussed. And ln K side, where slope is meeting to the y-axis vertical line, then that is called intercept. Then here intercept means intercept is equal to ln A, means from 0 to that point, maximum point where this H is hypotenuse is touching, then 0 to that point, that is called ln A, correct? And slope also you will get. And what will be the slope value? Then you know slope means tan theta. Slope means tan theta is equal to perpendicular P upon B, perpendicular by base. Then now, because all data you have drawn the graph ln T versus 1 upon T, then P value will get from the ln K values. Okay, ln K value 0 to up to ln A, what was the value that you will get, that is the P value. And down where it is touching this H, where it is touching on x-axis, then 0 to that point, that value will tell, that value of 1 by T will tell about the B base. And say P and B both you are knowing, and slope you can calculate. P by B is equal to tan theta. Tan theta is equal to slope, and slope is equal to, now you got minus Ea upon R. Then now R value is fixed, hence slope you are knowing, slope value you are knowing, that is equal to minus E upon R. R value you are knowing, hence out of 3, 2 value you are knowing, the third value, that is the Ea, easily you can understand, you can know, you can calculate. Okay, then at temperature, see now you are comparing two temperature you can use. At temperature T1, what is the value? At temperature T2, what is the value of rate? At temperature T1, rate constant will be different, and at temperature 2, rate constant will be different. Then suppose at T1 temperature, what is the rate constant? Means ln K1, Then at T1 temperature, ln K1 is equal to minus EA upon RT1. RT1, T is the temperature, T1 plus ln A. ln A is the constant. Then this is the first expression at temperature T1, and same way at temperature T2, what will be the value? Then ln K2. At T2 temperature, K will be T2. Then ln K2 is equal to minus EA upon RT2 plus ln A. Correct? Then two temperature you have considered, two equation you got. Here you want to know effect of temperature. That's why two temperature you are considering, T1 temperature and T2 temperature. Okay, initial temperature and final temperature. Means in the beginning, what was the temperature? Suppose 25 degree, and after 10 degree have increased, now 35 degree. Then that temperature, what is the K2 value at both temperature? Then now it is a simple mathematics. Both equation you add it. Then what we will get? Actually, A is a constant, A is a constant for a given reactant, for a given reaction. Then K1 and K2 are the, and K1 and K2, K1 and K2 are the values of rate constant at temperature and T2 respectively. Okay. Now, just because now ln A value should cancel, then you have to subtraction you have to do, no addition, subtraction you have to do. Means from second equation, first equation you have to deduct. Means from the K2 expression, K2, from the K2 K1 expression you have to deduct. Okay, ln K2 is equal to minus E2 divided by RT2 plus ln A. You write upside, and down you write ln K1 is equal to minus EA upon RT1 plus ln A, and do subtraction. Then what will happen? First ln A will be cancelled out, and then you will get ln K2 minus ln K1, that is equal to EA RT1 minus EA RT2 you will get. Okay, ln K2 minus ln K1 is equal to EA RT1 minus EA RT2. If you will subtract, then now after that all things are easy. ln K2 minus ln K1, that you can write ln K2 upon K1 by log rule. Okay, ln x minus ln y is equal to ln x upon y. By using this formula, ln K2 minus ln K1, you can write ln K2 upon K1, that is equal to, now EAR is common, you keep it outside. Then EAR, you have taken outside common, then in bracket what is remaining? 1 upon T1 minus 1 upon T2. This is actually formula. This is the formula, easy formula. You can remember 1 upon T1 minus 1 upon T2. For this formula we will use in solving the numericals. And after that simple, it depends upon your wish that you can convert ln, you can convert in log also. Then you know that you have to multiply by 2.303 if you want to convert in log. It depends upon you, your wish. Otherwise you have to remember this, ln K2 upon K1, that is equal to EA upon R in bracket 1 upon T1 minus 1 upon T2. This is important. This is the only important thing. But if you want to convert in the log term, then you can do ln, you convert in log, then 2.303 you have to multiply. Then ln will convert to log. Then log K2 upon K1 means what? Just 2.303, it will come to the right side down. Okay, then it will come EA divided by 2.303 R, and in bracket same thing, 1 upon T1 minus 1 upon T2. And again, if you want to simplify 1 upon T1 minus 1 upon T2, then easily you can write T1 and T2 take LCM you can take, and through simplification then you will get, finally you will get log K2 upon K1, that is equal to EA divided by 2.303 R in bracket T2 minus T1 divided by T1 into T2. Simplification 1 upon T1 minus 1 upon T2, T1 T2 down you can write as LCM you have taken, and then T2 minus T1 it will come. Then here you got the relation between K and T at different temperature. At different temperature, at T1 temperature, K value was K1, and T2 temperature, K value was T2. Then you got the relation. This I have discussed. This is very, very important. And next class I will solve the numericals, and other points are there, other terms I will discuss. That is the effect of catalyst I will discuss, and also I will discuss collision theory. Okay, collision theory of chemical reaction. This is the last portion of your chapter. Thank you.